All right, we are talking about the formal description of a DFA. Let me just refresh our memory. A DFA is, formally speaking, a 5-tuple. You know, if I call the machine M for machine, Q, sigma, delta, Q naught, and F, where what these represent, this is the set of states, is the big Q. The sigma is the alphabet. The delta is the transition function. The Q0 is the starting state. And the F is the set of acceptance states. All right. And if I tell you all those things, then that's enough information to draw the diagram, and then you can answer any questions you like based on those 5 basic ingredients of the DFA. Remember, so the most interesting or complicated part of this is the transition function, which is a function. The domain and codomain are like this: Q cross sigma to sigma. That means what you plug into the function is a pair, where the first part of the pair is in Q, the second part is in sigma. That is a state followed by a letter. So it, in practice, looks something like, D of S1 comma A means where do you go if you're in state 1 and you see A? You go to some other state, right? State 3 or something like that. This is typically what the transition function looks like when you write down one of its values. All right, and each arrow on the diagram corresponds to one sort of particular value of the transition function. All right. What I want to talk about today is I want to revisit other concepts that we've talked about so far and see if we can reframe them in this more formalized description. So, a string. Oh, sorry. One other thing that I wanted to remind us of from last time. We also have what's called the extended transition function. Extended transition function. And that is written as delta star. And it really represents the same thing as delta, but you're allowed to plug a whole string into it. So delta star of, it would look something like delta star of S2 ABAA equals S4, something like that. And what that means is if you start in state S2 and you read that whole string from there, ABAA, then it ends up in state S4. This is called the extended transition function. The only difference is what you plug into it here is a string rather than a single letter in the case of the ordinary delta. All right, that's the extended transition function. And this has properties, for example, delta star of, what was the first property? Oh yeah, delta star of any state in the empty string is just that same state. That means if you start in a state and you do the empty string, you end up in the same state because you didn't do anything. And then there was this other weird property about if I start in some state and I do a string consisting of some string x followed by another string y, the effect of that is you start here and you do x, and then from there you continue and do y. And the way to write that, I think we said this at the very end last time, which is pretty weird looking. Oops, Q here. It means if you start in state Q and you do x followed by y, what that means is first I start in state Q and I do x, and whatever that state is, I start there and then I do y. And I end up with some destination. All right, those are the two important, kind of obvious, although the second one is very strange looking. It makes a lot of intuitive sense if you think about it properly. All right. What I would like to talk about is a formal description of what it means for a string to be accepted, right? Let's say x in sigma star, that's a string, is accepted when, what that means is if we start in the starting state, I'm just going to write it in words first. Before we started talking about all this formal business, if someone asks you, what does it mean to be accepted? It means if you start in the starting state And then you read X as a string, one letter at a time. Then we end up in one of the accepted states. And we end up in an accepting state. Actually, all those words can be said using this formal business about the sets and deltas and whatever very easily. I mean, it looks compact at least when you say it. X is accepted when... Anybody think you can say this in terms of all of this symbology we got up here? These things here? Deltas and whatever. What you want to say is, if you start in the starting state and you read X, then you end up in the accepting state. Any thoughts about that? How can I say that with all this formal language? Here's a hint. You should use delta star. You use delta star to say something like, if I start here and I do this string, this is where I end up, right? That's sort of what I want to say something like. Any ideas? You can give me a half idea if you like. What do you think?
We could do something like delta star and then like the Q0.
Yeah, huh? Yeah, that's the starting state.
The F.
Okay, yeah, great. So this means if I start in the starting state and I do X, then what? You don't want to finish? Yeah?
Equals F.
Okay, this is almost right. Although not exactly. Equals F. Yeah, that means, what you mean by that is when you start in the starting state and you do X, that is an accepting state. Right?
From F.
Yeah, instead of equal doesn't quite make sense here because F is a set of states, whereas the thing on the left side of that equal sign is an element. You got to say is an element of F. Right? F is the whole set of accepting states. So what I'm saying is, this is the state we arrive in after reading X. Right? Starting in the starting state and you read X, that's what the left side represents. And then it says that this in ordinary language is an accepting state. F is the set of all accepting states, and we're saying that thing is one of those things, one of those accepting states. All right? Excellent. So this is... that bunch of nonsense is equivalent to all of these words, right? It looks fancy. This is like Hollywood math. They like this thing. They like that, the delta. They like anything that looks kind of crazy. All right. This is the formal definition of what it means for the string to be accepted. And so we can give a formal definition of the language of a DFA. If M is, Q sigma delta Q naught F is a DFA. Here's the definition. Oops. DFA. Then this is a definition. Then the language accepted by M. This is the true definition of the language accepted by the DFA. Is L of M is, it's the set of all X, set of all strings, which have this property in the box. So I'm going to say the set of all X in sigma star, that is any string with the appropriate alphabet, such that, and now I'm just going to write what it says in the box. Which means when you start in the starting state and you do X, it ends up in one of the accepting states. There you go. This is the formal definition of the language accepted by the DFA. It looks very fancy when you write it like that. Any questions about that so far? Yeah.
So the sigma star is like X is an accepted string.
Sigma star just means any string. So this says x is any string, and then
Okay.
the bar means such that, and that over there means x is accepted.
Okay.
Yeah. Accepted by the DFA. All right. This is all a bunch of formalism, which usually we don't think of it in terms of this way. That's what I said that several times last time. Even though the DFA, its true nature is that 5 tuple, you're still gonna usually think about it in terms of a diagram. What's useful about this is this formal language, this formal approach is necessary to actually prove things about DFAs. Because without the formal approach, all you have is the picture, and it's difficult to write a real proof just by pointing at a picture, all right? That's the problem. That's sort of why this point of view is necessary. Even though, as I always say, you still usually are going to think of it like a picture. But if you want to actually prove stuff about DFAs, what I wanted to say, you really need the formal approach. Otherwise, you find yourself just sort of like saying things about a picture, which is not a good way to prove things. I wanted to do one example like that, and you'll see just how the formalism is helpful, although it is pretty technical if you really want to get into the details. Here is one example of proving something about DFAs. You know, all the questions that you did on the homework, and even the ones on the quiz here, like I said, I drew that DFA and said, tell me what the language accepted by the DFA is. None of you wrote a proof, right? You just like told me. It has no B's or one B. That was the answer. If you actually wanted to write a proof of that, you basically need this formal language in order to write your proof. Otherwise, you don't have anything to like get started with other than just looking at the picture. So this is a simple example of a DFA where I'm actually going to prove what the language is using the set theory. You have to use the set theory because there isn't any other real way to write your proof in detail. All right. This is a DFA using just the alphabet sigma equals A, just A. So all strings here are just a bunch of A's. All right. And let's prove, like really prove that. Let me just say, I don't know if all of you guys are into proofs. I'm kind of into proofs, I suppose, in my own personal life. But we're actually not going to do a lot of proofs in this class, so I hope you're not turned off by the idea of proving this. Anyway, let's prove that the language of this machine is, it's all, can anybody say in words what the language is? I mean, it's all things that look like A to the N. That's just because every string possible in this language looks like A to the N, because I only have one letter A. What's the property? To the right of the bar, I'm going to write something about N here. Yeah?
And it has to be divisible by 3.
Yeah, N is divisible by 3. So I'm going to write that as, I'm going to write, would you mind if I write it this way? N is 0 mod 3. In this particular example, it's more convenient to talk about the modi mods. All right. That, of course, means N is divisible by 3. Let's try and prove it. So what I got to do is somehow demonstrate that N equals 0 mod 3 is what you get from this stuff up here, right? If I were to write out this business in the context of this problem, I would get this set. That's what we need to argue somehow. D star of QX is in F. That's the same as what this says down here. So what I want is, I want to show that this set, A to the N, such that N equals 0 mod 3, is equal to the set of a to the n's such that delta star of the starting state. Now, I don't have names for any of my states. I'm going to call them Q1, sorry, I'll call the first one Q0, Q1, Q2, all right? Last time I called them S's. Sometimes I call it S's, sometimes they're called Q's in our book. Whatever, call it whatever you want. Anyway, I called the starting state Q0 though. That's a, you can call it whatever you want, but if you're going to call one of them Q0, it should probably be the starting state. And what I have to show is that a to the n such that n equals 0 mod 3 is equivalent, is the same as the set of a to the n such that delta star of q naught and a to the n is in the set of accepting states, which in this case is just Q0. All right. Sorry, I kind of ran out of room over there, but I'm trying to copy down the formal definition of what L of M is. It's off my screen at this point. It says delta star of Q naught x. In this case, every possible x is just going to look like a to the n. Is in the set F. Now, actually, this we can simplify immediately a little bit over here. Rather than saying an element of that set of one element, you can just say that equals Q0, right? I want to say that this is the same as delta star a to, sorry, I got it backwards, Q0, comma a to the n is equal to Q0, all right? What we have here is we need to show that this set over here and this set down here are equal to each other. And that's actually the same as just showing the thing to the right of the bar each time, that those are equivalent. So it's enough to show, I'm going to say again, I want to show that n equals 0 mod 3 if and only if delta star Q0 a to the n equals Q0, right? This is what needs to be proved. That those two conditions which define the sets in both cases, they're actually the same. They're equivalent to each other. N equals 0 mod 3 is equivalent to delta star of Q0 and an equals Q0. All right, can we do that? We got to say something about delta star of Q0 and a to the n. So I'm gonna. This is what we want to show. So far I've just been rewriting over and over again what we want to show. Although now I'm actually going to start saying something about actually showing that. In order to show that, we need to sort of unpack the thing on the right side. That delta star is kind of complicated. What is delta star of Q0 and a to the n? All right. Maybe we could just sort of try to do some simple little examples. Delta. Well, let's just look at delta of Q0 and a. Delta star is sort of what you get by doing these deltas over and over again. So maybe to try and understand this, we could just say, what is delta of Q0 and a? What do you say? I mean, you can look at the diagram. It is Q1, right? That's what that is. And delta of Q1 and a is Q2. And delta of Q2 and a is Q0. All right? This is from the diagram. Now, I said it's not really, we don't usually like to write proofs in terms of the picture, but really, this isn't exactly from the picture. This is actually the true nature of the DFA, right? So when I say these things, I'm not actually referring to the picture per se. I'm referring actually to the DFA as it truly exists as a bunch of sets and functions, all right? So anyway, those that's how the delta works. Check it out. I will have you notice, note, you can actually generally say delta of, let's say, Qi and a. If I'm in state Qi and a, what's the effect? Like, look at those numbers over there. What happens when you're in some state and you do a? Can you say in general? Yeah?
I plus 1.
Yeah, it's Qi plus 1, where you just have to allow me to say with the subscript mod 3, right? Because when you're at state 2, you go back around to 0. So when I say this, dqia is qi plus 1, that's true as long as you read the subscript all the time, mod 3, all right? Okay, great. I think then, can we say, in even more generally, what about this? Delta star of qi and a squared. Can we say, I want to say something similar to that formula up there. If I start in a particular location and then I do a squared, what is that going to be? Q, I'm going to fill in something down here. Yeah?
I plus 2 mod 3?
Yeah, I plus 2, where again, you have to go mod 3 in the subscript. If it gets too big, you wrap it back around again. I'll just say mod 3. I mean, mod 3 in the subscripts. Those are the only things that are actual numbers in this problem are the subscripts. All right? Etc. Right? In fact, I think we can say delta star of qi and a to the n is qi plus n, right? If you read n different i's, each one of them just adds 1 onto the subscript. And so if you add them all up, you get qi plus n. Again, mod 3. All right? Actually, that, I put little ... and then said this. I hope that you all agree with me. This is true. Although, technically speaking, if you really want to do this proof in full detail, you have to prove that step by induction. Where this right here is the base case. If you only do it once, you get this formula. If you do it n times, you get this formula. I don't really want to go into the details of the proof by induction, but it is lurking underneath. Okay? Anyway, I don't know if you're, I hope you're not lost at this point. I'm just writing something fancy, but actually this is pretty much the end. Check it out. We have this, right? Which looks quite a bit like that right there, doesn't it? What this means is, in particular, if the I there is 0, because if you look in the box at the top there, it looks like that, only the I is 0 is the only one we really care about. So for I equals 0, what this says is delta star q0 a to the n equals q0 plus n, which would be just n mod 3. And so, I could say delta star of q0 and a to the n equals, when exactly is it going to equal q0? Well, according to this, it would be whenever that subscript ends up being 0 when you go mod 3. That actually happens if and only if n equals 0 mod 3, right? The answer to that delta star is always going to be qn. Now, when is that actually equal to q0? It's when n is 0 mod 3. But isn't that, this is exactly what I said I wanted to show. I know I scrolled past it, but that is exactly what was in this red box here. N equals 0 mod 3 if and only if that stuff about the deltas. All right? And that is exactly what we wanted. Shun! This is what I like to write at the end of my proofs. I have an old real analysis textbook, like from the 19-teens. At the end of every proof, they write shun, which I think is funny. So, that's the end of this proof. Now, like I said, you basically never actually think of a DFA in this way. And if I show you this picture, I hope that you would say, like, just by looking at this picture here, I hope that in a sense you feel like that's kind of an easy one. It's easy to tell. It's accepted whenever the number of a's is a multiple of 3. You quickly forget that it was supposed to be easy when you find yourself having to do all of this business here. This is not quite easy to write down all the details. So this is not the kind of thing that we're going to be doing over and over for the rest of the semester. I just want to demonstrate this is the point of that formalized language, because looking at the diagram, you can convince yourself that things are obvious or things are easy, when really, if you actually try to prove them, you have to do quite a bit of work to write out the whole proof. We're usually not going to do it, but this is the point of the formal approach to all of this. It's why all the formalism exists, so that if you wanted to write a proof, you actually could, even though it's not easy. All right. Great. We got 10 more minutes left. Our next, we can start talking about the next kind of big thing that I want to discuss. I want to talk in some generality about regular languages. This is a word I used a few times ago, but I don't think I've said this word again recently. Regular languages. A language, of course, is just any set of strings. And remember, a regular language, anybody actually remember what this means? Is one which... Yeah?
It's the language of some DFA.
Yeah, a language which is the language of some DFA. I will just say a regular language is one which is, okay, I'll say it this way, accepted by some DFA. Right? For example, the set of all strings, remember the word language is basically a synonym for set of strings. The set of all strings which use either 0 or 1 Bs, that is a regular language, because you can make a DFA that accepts that set, and it was the one you saw in the quiz, right? That's a regular language. Big question that we want to answer, actually this is going to be an ongoing question for many weeks of this course. Which languages are regular? If I just show you a set, can you tell me if it's a regular language or not, a set of strings? Which languages are regular and which ones are not? And can you, demonstrate one way or the other? All right. What I want to talk about so far, so far we have many examples of regular languages. Basically, every answer to a homework problem about tell me what the language of this DFA is, those are all regular languages, because that's what regular language means. We have many examples of regular languages. Every time you ever write a DFA, it has a language, and that language is regular. What I want to talk about for the next, the rest of today, plus at least all of tomorrow, not tomorrow, next week, can we combine them and get more regular languages? Right? A language is just a set, so it's natural to ask a question like, for instance, if I have two regular languages, is the union of those two sets also regular? Is the intersection also regular? Et cetera, et cetera. There's lots of questions like that you can answer that are actually, interesting and meaningful questions. So we already have many examples. Can we combine regular languages and get more and more regular languages? And this, in some sense, is the same as the question like, what happens if I have two DFAs and I combine them together? Because if you have two different regular languages, they are each the language of some DFA. Somehow combining those two languages, you could also think of as somehow combining the two machines. And this could look like something like you plug one DFA, you make one DFA start where the other one stopped, or something like that. You can probably imagine some ways maybe you could combine two DFA diagrams together. All of that is the kind of thing that we're going to talk about for the next maybe at least a week. And I think we have enough time to do just a very simple construction. These will each involve some kind of way to change a machine into another one, or add two machines together, something like that. The simplest of all of these, let's think about, this is a very simple one, complements. This is something I'm sure you learned about in discrete math. The complement of a set. Anybody remember what that means? The complement of a set.
Is that just like everything that wasn't in?
Yeah, right. It's everything outside the set, everything that's not in that set. So if L is a language, I hope you don't mind me using, I use the word language and set interchangeably. A language. If L is a language, the complement, which in our textbook is written with a bar, L bar, that's the complement. Complement. L bar is, you could write it this way, the set of all x in the alphabet or strings such that x is not in L, right? L has a bunch of stuff in it. L bar is everything else. All the things which are not in L, right? And the first of many questions that we're going to ask about regular languages in this kind of context is, if L is regular, then what about L bar? For example, if I have L is the set of all x such that x uses at most one B. That was the language on the quiz today. Then L bar is the set of all x such that, how would you say in words what L bar is? I'm going to say, I'm going to write something over here similar to L bar. You want to say basically the opposite of that.
2 or more B's?
Yeah, 2 or more B's. X uses 2 or more B's. Now, the first one is a regular language because there is a DFA which accepts that language. What about the second one? Could you make a DFA that accepts L bar? Here's a DFA for L. It's that one that was on the quiz, right? I will just briefly rewrite it. They're not coming here. You can all jump out the window. These 200-year-old windows. Your time is up. Okay, this was the DFA for L, right? If you think about it, right, it's actually very easy to change this around to make it a DFA for L bar instead of L. We want it to accept only the ones that this one did not accept, right? It's got to be the opposite. Any suggestion? Yeah.
Flip-flop the accepted and the rejected.
Yeah, right. So to get a DFA for L bar, and this is not special about this example, this will always work. To get a DFA for L bar, we swap the accepting and rejecting states. All right? And so actually, you can say very nicely, if M, our original DFA was, Q sigma delta Q0F, if this has language L, then I want to sort of fill in the blanks, has language L bar. Think about, I'm going to write, the 5 parts again. Now, some of them are going to change around because I'm changing the DFA around.
I think that should be L bar, right?
Yeah, thank you. What I said up here, to get a DFA for L bar. Yeah, we start with L. Thanks. The point is, to get a DFA for L bar, we swap the accepting and rejecting states. If you want to write this more formally, if I have a DFA for language L, can I write the 5 parts out for the DFA which will have language L bar? You just have to think, in the new machine, how do I change the set Q, which is the set of all the states? Or maybe I use the same states. I use the same states, right? The new machine will have the same states. How about the alphabet? Same alphabet. Okay. How about the delta, which represents the arrows? Same arrows. Yeah, that's good because the delta is usually the most complicated part. Q0, the starting state, should be the same. You don't change the starting state. The set of accepting states. This will change, right? And what you have to do is sort of flip-flop. Everything that was accepting becomes rejecting. All the ones which were rejecting becomes accepting. Can anybody see how would I write that as a set? Q minus F. Yeah, that is all of the states which were not accepting. Another way to write that? Yeah,
F complement.
yeah, the complement of F. So you can write F bar. It's actually very, very cute that way, right? If you start with a particular language, how do you make a DFA that gives you the complement language? Everything's the same. You just take the complement of the F. Okay? Can I just say, I know it's time to go, but this all of this constitutes a proof of this theorem. If L is regular, then L bar is regular, right? Because there is a way to get a DFA for L bar. You just do what I just said. You swap the accepting and rejecting states. All right, we'll have more things like this next time.